last week we looked at how the 4 different ways that we can deliver traffic, deliver data across a network using unicast, broadcast, multicast and anycast. And we looked at a bit of detail of how IP multicast works. That IP multicast we'll see is important for some multimedia applications, because think of streaming, where you have one source that streams video or audio to multiple destinations. Then rather than having multiple individual separate unicast streams, have one multicast stream. There's a source, the server, that uses utilizes multicast inside the network to the source just sends one copy of the stream, and the network delivers copies to all of the destinations that want to subscribe to that stream. For example, looking at watching TV across the internet, IPTV. So that's one thing, multicast is one thing that's important for multimedia applications. Another thing that's important is quality of service, which is really trying to differentiate the service that we give to different applications, or at a finer level of detail to different packets. We'll go through the concepts of two forms of quality of service, 2 different approaches that we can use. A basic explanation of how it works is like when you drive into Bangkok, what is the main thing that contributes, if we look at performance from the perspective of delay, that is when you drive into Bangkok, you care about how long it takes to get there. Well, when you drive in there, the main thing that may impact upon delay, that is makes the delay variable, may be traffic congestion. For example, at some of the stoplights along the way, if you get to a set of stoplights and you have to wait for 5 minutes, then that 5 minutes contributes to your total delay to get to Bangkok. Why would you have to wait for 5 minutes at that set of stoplights? Because there's a lot of other traffic going in the other directions, for example, going across. Sometimes when you drive along the road between the stoplights, you can go fast, but then you come up to the intersection, then you need to queue up at the intersection, wait for that 5 minutes, and then once you go through that intersection, then you can go along the road at your normal speed, then you get to the next intersection, then you wait, and so on. So we can think as, in that case, the thing that contributes to delay significantly is the queuing time spent at the intersections, at the stoplights, for example. So how do we reduce that queuing time? If we have to take the same path, we cannot go on another route. How do we reduce the queuing time? How do you get through the stoplights faster? You put on a siren, okay? If you're a policeman, then you can bypass the stoplights. Well, in some cases. Let's say that at some intersections there's a policeman working the intersections. He presses the button to turn it from green to red. Normally he does that just based on, okay, 5 minutes on red and then 5 minutes on green. If he sees another policeman coming, sees the lights flashing, the siren going, then the one that's working the stoplights may automatically switch that to green and allow that policeman to go through. So, or he bypasses, he goes around the side of other cars and goes through the red light. So that's one way to avoid the queuing delay, is to give priority to a special user in this case. So emergency services get priority in this case, and therefore the time that they take to get from source to destination is shorter than the normal user. They get priority. They get a higher quality of service compared to normal users. And we'll see that that's one approach that we'll use in the internet. As we recognise, when we come to the internet, the congestion normally occurs at the routers. So at the routers, as we recognise packets coming in that need higher priority, will let them jump to the head of the queue, for example. They don't have to wait in the queue, they can jump to the head of the queue and go out first, therefore giving those packets shorter delay. That's one example of quality of service. So for that to work, we need to be able to identify which packets need priority. In our car analogy, then the policeman or the police car is identified based upon the painting on the car, the siren and the lights. How do we identify packets as to how do I give Steve's packets more priority compared to all the students' packets? So we need to be able to classify the packets. And then once the packets are in the router, we need a queuing mechanism to allow some packets to go to the head of the queue, for example, rather than having to wait at the end. We'll see that. So that will be one approach to quality of service. Classify packets and give them priorities in the queue. What's another way that you can get from here into Bangkok faster, avoiding the congestion? One way is that, okay, as a police car arrives at the intersection, if there's a policeman working at the traffic lights, he can change the lights or he can direct the police car to bypass everyone else. That is, to go to the head of the queue, and therefore he gets through faster. That's one approach. What's another way to make sure that, let's say a police car wants to get from here into Bangkok very fast? What can it do? Maybe he's directing some very important person. What do? You have a VIP in some convoy of cars coming along from here into the centre of Bangkok. They close all the roads, okay? So, in fact, what they do in advance, probably days in advance, they know that someone's going to be going along that route. So they, in advance, go and close all the roads, set up the traffic lights such that they'll be green all the way through, that no other cars will be able to come in there, and therefore they have a clean run from the source through to destination. They just go straight through all the traffic lights. So in that case, again, they get priority compared to other users. They get high performance, or they get a higher quality of service, a low delay. And how does it work? It requires some information in advance. That's very complex, very time-consuming to set that up, because it needs to be organised that someone's going to be taking that path. They need to close off the roads all along the way and so on. So it's very complex, but it works very well because the user gets the guaranteed quality of service. You can basically calculate how long it will take to get from source to destination. If you know all the roads are open, then it's simply to do with the distance divided by the speed that you travel. You can calculate the delay in that case. So it's very accurate in giving some level of service, but it's very complex to set up. And of course, it may cause problem for other users, the normal users. So two approaches there. The first one is almost on demand, as coming back to the internet, as packets arrive at routers, classify them and give them some priority in the queue, higher priority as needed. The second approach is, before you start sending packets, set up along the path reserve some resources along the path, because that's what happens with this VIP, that they reserve resources. That is, they make sure the traffic lights will always be green. They reserve resources along the path beforehand, and then your packets can go straight through. And we'll see, and we'll give names to these two different approaches as how we can use them for quality of service. The internet doesn't have inbuilt quality of service. That is, it doesn't by default give priority to any packets. It's considered a best effort service. That is, IP is a connectionless protocol using packet switching. We just send IP packets, send it to the next router, that sends to the next router, and so on. By default, we think that there's no priority given to any packets. Every packet is treated the same. It's what's called a best effort service, because the network makes its best effort to deliver those packets to the destination. If they're not delivered, too bad. It's not the role of the internet protocol to fix that. And if some have a large delay, too bad. Again, it's not the role of IP to give guaranteed delays for packets or guaranteed performance. TCP adds some reliability but still offers no guarantees on performance. You transfer from here to some web server, the performance that you get is not guaranteed when you set up that TCP connection. It may change from today compared to tomorrow. But of course, in some cases we would like performance guarantees. We'd like to make sure that we get a particular download speed or a particular delay is incurred. Some examples. If you're watching TV over the internet, IPTV, and you're watching digital standard or close to high definition TV, you want high quality showing on a large screen, not on a laptop screen, then you need high resolution. You may need a sustained throughput of about 6 megabits per second. That is from the source server to your house where you're streaming the TV. Then the throughput of that connection while you're watching that TV needs to be about 6 megabits per second in some cases. If it goes below 6 megabits per second, down to 5, 4 megabits per second, even for 10 seconds, then that may mean that your TV will start to freeze. So when you're playing a movie, it'll start to freeze, or you'll start to lose some packets, and you'll see artifacts in the output on the screen. Of course, most users will not accept that for a TV service. With a TV service, normally we'd expect high quality all the time. So if we want to provide the equivalent to our normal broadcast TV, but over the internet, then we may need some quality of service to make sure that we get sufficient performance. Another example, a voice call. You make a voice call, a voice over IP call. The delay between you and the other person you're talking to is important. If there's a large delay, then it's very hard to converse, because you say something and then there's a delay for the other person to hear that, and because there's a delay, then they start talking at the same time, and it turns out you both start talking at the same time if there's a large delay on the phone line. So with a voice over IP call, we usually require delays less than 100 milliseconds. We can tolerate maybe 200, even up to 300 milliseconds, but 500 milliseconds, 1 second, and it starts to become too hard to have a conversation. Jitter is also important. Remember, jitter is a variation of the delay. That is, if the first packet has delay of 100 milliseconds and the second one 101 and the third one 102, it's the difference between that 100 and 101, 101, 102, and the average of those values. We'd like that to be small as well. That is, if our delay is 100 milliseconds, I would be happy if all my packets have a delay of 100 milliseconds. Not 99, not 101. It would be better if all of them have a delay of 100 milliseconds. So we'd like some performance guarantees to make sure our voice call works well for the user. And there may be other applications. Maybe you're transferring large medical data. You may want to make sure that you don't lose too many packets in the network. Some businesses may require a minimum data rate so that they can perform their normal business operations when communicating with, say, servers and with other offices that they may have. And some of the things that they may specify as a performance requirement is a minimum throughput of, say, 2 megabits per second, and some average throughput. So on average, over a period of 24 hours, they may require 3 megabits per second, but they may tolerate that, okay, sometimes it will go down 2.5 megabits per second, maybe down to a minimum of 2 megabits per second, and they can tolerate that. But if it goes less than 2, then that may be a problem for their business, for example. If it goes above, that's okay. So different users and different applications may require performance guarantees. How do we provide that? Because IP doesn't provide it by default. QoS, or quality of service, refers to statistical performance guarantees that some network can make. The most common measures are packet loss, making sure the number of packets lost is below some level, delay and jitter, making sure the delay and jitter are below some levels, and throughput, making sure that our throughput is above some level. So provide some performance guarantees using these example measures is what quality of service does. Statistical, we'll see that by statistical we'll often refer to average performance guarantees or average over some period of time. Maybe we don't care if every packet has a delay of 100 milliseconds, so long as the average across or some statistical measures of that delay averages out to 100 milliseconds plus or minus 5 milliseconds. So we don't always care about the instantaneous values. Most times it's the average value. How do we provide such performance guarantees? What mechanisms are available? We'll see that there are two basic approaches, or three in fact listed here. Hard quality of service, soft quality of service, no quality of service. Okay, no quality of service, we don't do anything about it, just the default approach. When do we need quality of service mechanisms? We need QoS when network utilization is high. Then if I have a very simple case, if I have a single link, so a very simple network, a link which has a data rate of 100 megabits per second, an Ethernet link, and the application you're using, the delay across that link is less than 1 millisecond. It's just a direct cable. It's in the order of hundreds of microseconds. You're, not a good example, but you're using a voice call between source and destination, or streaming audio or streaming video even. Quality of service is of no interest to us in this case. Our voice call needs delays in the order of tens or hundreds of milliseconds. It can tolerate delays up to 100 milliseconds. Our link or our network has a delay of less than 1 millisecond. We don't need to do anything to make this application work any better in this case. We don't need to control quality of service. We don't need to give priority to our voice application. In this very simple situation, we will get the performance guarantee that we require. We start sending the voice traffic. The delay is going to be very small because we have a fast link with a short delay. We have no intermediate routers. If we need a bandwidth of 100 kilobits per second for our application to work well, then we're fine. Our capacity is 100 megabits per second. If we require just 100 kilobits per second, then there's sufficient capacity available for our voice call. The utilization of that link with just one application running across it is very low. We don't need any quality of service in this case. Let's make it a bit more complex. Introduce a router here, and there are multiple computers connected to that router. Let's say all the links are the same, 1 megabit per second, and all have a delay of about 1 millisecond across the link. All the links are the same, and we're sending some video, we're using some video application from A to B. And for our video application to work well, let's say that we need to get a sustained throughput of 600 kilobits per second. Let's forget about delay. We care about the throughput in this case. We're going to stream video. To get high quality at the receiver, we need to send at a constant rate or a sustained rate of around 600 kilobits per second. If no one else is sending, that should work okay. Each link supports 1 megabit per second. We start sending at 600 kilobits per second. The router receives that and immediately forwards on to B over this second link, which also supports 1 megabit per second. So that's okay for our video in that case. But what if these other computers start sending? C starts sending data to other computers via that router. Then, and they also start sending not just to the router, but also to B. They start utilizing this link. If the amount of traffic they're sending is all around 500, that's a 5, doesn't matter, kilobits per second, and that traffic is all going to B, then what's going to happen for our video application going from A to B? If we evenly share amongst all the connections, if let's say they're all sending to B, then B has 600 plus 500 plus 500 plus 500, 2,600 coming across this link. The link only supports 1 megabit per second. It cannot support all of that traffic coming across this link. So normally we would divide the capacity of the link amongst the different sessions. So there are 1, 2, 3, 4, 5 sessions being sent across this link. If we were using TCP, in the ideal case it would divide the capacity amongst those 5 TCP connections. That is, A to B will get 200, C to B will get 200, D to B 200, and the other two also 200. They would share that 1 megabit per second or 1,000 kilobits per second amongst the 5. So A to B gets 200 kilobits per second, but we required 600 kilobits per second. That's the problem. The utilization of our network is high in this case. To make sure that our video gets 600 kilobits per second, we need some quality of service mechanism. For example, to give priority to video. Let's say the traffic C and D is generating is web traffic or some file transfer. We want to give priority to a video session. Then what we'd like to do at the router is to say all the packets belonging to this video session coming from A to B, give them priority when you send them to B. Make sure they are sent first. So that of this 1 megabit per second, 600 kilobits is allocated to our video. The remaining 400 kilobits is allocated to C, D, E, and F. That would be one example where we give priority to one application by applying quality service mechanisms. So, we need quality of service when our network utilization is high. If it's low, then it's of no, we don't need it. It doesn't matter because we will meet our requirements. The idea is that our applications have some requirements in terms of performance. The network needs to run such that those requirements are met where possible. If the utilization is low, then those requirements will always be met. But if the utilization is high, then it will be harder to meet those requirements, and that's when we need to start giving priority. And the two approaches that we give priority or provide quality of service are like we said at our start example, where the policeman either comes to the traffic lights and at that set of traffic lights he's given priority, or in advance we reserve the roads from source to destination. Hard quality of service or guaranteed quality of service is where we reserve the roads. That is, we reserve resources from source to destination before we start sending packets. Before A starts sending packets to B and before all the users, then they perform some special operations to tell the router, to tell B, I want to start a video session and I need a guaranteed performance of 600 kilobits per second. Please reserve enough resources in the router and across the links so that I can send it 600 kilobits per second. The network will say, yes, I will reserve that for you, and then guarantee that performance. Or the network may say, no, I don't have enough resources to do that. So we'll go through that one of hard quality of service. We guarantee quality of service. If a user requests 1 megabit per second from some network, a network operator, then if that request is accepted, then the user will be guaranteed that performance for the duration of their session. Of course, the request could be rejected. So we reserve resources for users. The other approach is on demand, where we don't provide any reservations, but we try to provide relative performance guarantees. It's called soft quality of service or service differentiation. We simply differentiate the different users. The idea is that a user may request or want 1 megabit per second of performance for their application. The network will try to provide that by giving priority to the packets from that user. But in some cases, it may not guarantee that 1 megabit per second. It may drop below. We'll see that, of course, hard quality service is better from the user's perspective. To guarantee performance is better than to say, yes, I'll try to give you that performance, but sometimes you will not get it. But providing hard quality service is more complex because it requires some setup in advance. So we'll go through both of those approaches. The other approach is no quality of service. Let's look at soft quality of service because we'll see some of the mechanisms that we use here are also generic across both approaches. The idea is to give priority or different priority to different types of traffic in the network. Let's just jump forward and see if we have a diagram. Okay. When we talk about different types of traffic, then there's different levels of detail that we can deal with. We can talk about a flow or a session, which usually means for a single application or pair of applications from source to destination. So our video application communicating from A to B could be considered one flow in the network or one session in the network. A video call from A to F at the same time would be a second flow in the network or a second session. So flow or session in our case are the same. If I'm transferring a file from C to E, that's another session. So we would like to give priority to individual sessions in the network. For example, give our video session higher priority, give all other sessions normal or low priority. Or give the video session highest priority, give a voice session from C to E medium priority, and give all other sessions, web traffic, emails, low priority. So we can refer to individual sessions or flows. Or in some cases, when we don't want that level of detail, we can refer to a collection of flows or sessions at what's called the class level, an aggregate of flows, a collection of flows. Give all voice calls high priority and give all FTP downloads low priority, as an example. So it's not about an individual voice call. Every voice call gets the same level of service. That's easier from the network's perspective because we don't care about individual flows. We just say that everyone who's making a voice call gets the same performance. So refer to a class level. We have a class of applications or a class of service. Or all voice traffic gets high priority, all non-voice traffic gets low priority, as another example. In the internet, the technology that, or the name of the standards that were created that aim to provide this quality of service in the internet is called Diffserv, because we'll see that we'll differentiate the service offered to different flows or classes. Differentiated services, short name Diffserv. It's an architecture that provides service differentiation. In practice, it's normally applied on the class level. Because in the internet, there are many different flows in progress. If you look at across the core networks, to manage quality of service on an individual flows basis is very complex. You need to keep track of all of them. It's easier to manage quality of service based on a collection of flows. That it's class-based service differentiation. That is, all voice traffic gets one level of service, all web traffic gets another level of service. As opposed to Steve's voice traffic gets the highest, user X's voice traffic gets the second highest, and so on. That's more complex to perform when you have many different users. So in Diffserv, normally applied on the class level. Normally provided by internet service providers within their network. For example, your internet service provider could treat all packets that are marked as voice packets with some priority level, whichever they choose. And all other packets, maybe they give a lower priority level within the ISP's network. Let's see some examples to see what we need to do for this to work. Here we have a simple network. We have host 1 wanting to send to host 3, host 2 wanting to send to host 4. We have two routers, router R1 and R2, and the link between them is the bottleneck. Capacity of 1.5 megabits per second. By bottleneck, it means that these other links are much higher. The one link that slows us down is between R1 and R2. If the sending rate of H1 and H2 exceeds in total 1.5 megabits per second, we're going to have problems with performance. Looking at R1 in detail, there's router 1. We can think we have coming into router 1 from the traffic from H1 and the traffic from H2. And coming out of router 1 is the link that goes to router 2. And that supports 1.5 megabits per second. So the data rate, 1.5 megabits per second coming out. And the router actually has normally input queues and output queues. I'll draw that larger because we'll focus on the output queue. So a space in memory where as our packets come in, they're stored in memory and processed and then sent out. So a queue, and there's some processor that a packet comes in, is put in the input queue, the processor looks at it, looks at the packet in the head of the queue, determines where to send it, and in this example, all packets are being sent out to this queue and puts it into the next output queue. Of course, if there was another link going out, say to R3, don't draw this, then that would have its own output queue. So what the processor does is, as a packet comes in, It looks at the packet at the head of the queue, decides which output queue to send the packet to, depending upon the routing. But in this case, the routing is simple. Send everything to R2. So packets are coming in and all going out to R2. This is our queue or buffer. If packets are coming in at a rate of 500 kilobits per second on this link and 500 from H2, then we can think over time packets come into the input queue, processor puts them all into the output queue, so packets come in, put into the output queue, and because our output capacity is greater than the sum of the input, the packets, once they go into the output queue, are sent with very small delay. The input, or the aggregate of the input, is less than the aggregate of the output, and therefore the queuing delay is very small in this case. Of course, on average, these may represent the average sending rates or input rates. In real life, it may go up and down. There may be a burst of packets come in, and then nothing comes for a short period of time. So 10 packets come in over a period of 5 milliseconds, and then 3 packets come in over the next 10 milliseconds. So that there may be varying over time. So we just talk about the averages here. So there may be some queuing delay. Packets from H1 come in, are queued, and packets from H2 may be in the queue. But on average, because the average input is less than the output, then the queuing delay will be 0 or small. Where say the black ones represent packets from one source, H1, and the blue from another source. They're basically queued and sent immediately. But of course, as the input rate increases, we're going to have problems. If they're both sending at 1 megabit per second, the output's only 1.5 megabits per second, what's going to happen? The packets will enter the queue, and because we cannot send out fast enough, the queue will build up, because we have a total of 2 megabits per second coming in and only 1.5 coming out. So every second, how much data needs to be dropped? The queue is going to fill up. Let's just focus on the output queue. Packets come in and put in the output queue. Eventually, the queue is of a limited size. It fills up. Another packet comes in. When it's full, what happens to that packet? What happens? It's lost. Let's say the packet comes in. The router sees our queue is full. That packet is discarded. Let's say it lost. We discard that packet. On average, how much traffic are we going to lose per second? How much? 0.5 megabits per second. We have 2 megabits per second coming in, 1.5 going out. Where does the other half a megabit per second go? It's lost. Okay? So on average, we're losing half a megabit per second of traffic. So there's our problem in this case. A, the packet delay increases because packets spend more time in the queue, so the delay increases. And B, packets are lost because the queue will eventually fill up and packets will start to be dropped or discarded. So 2 problems there. Packet delay goes up, packet loss goes up. So even the packets that get through are delayed more than in the previous case. So that's without any quality of service. So let's consider what happens if we have two different applications here. We have one application which is a video application, sending video from, what are we doing? The picture and the example from the textbook had a voice application. I'm making a video application. It's not a voice call, it's a video call, for example, where we require a throughput of 1 megabit per second. If the throughput is less than 1 megabit per second, then the video quality will not be high enough. And as a user, we will not be happy with the service. And if we're not happy with the service, we may go and pay another, we may leave this ISP and go pay another service operator. So that's bad for business, or alternatively, I will not use the video application. Bad for the user. So for our video application to work, we need 1 megabit per second of sustained throughput. And low delay and packet loss. Again, if we lose packets, the quality at the receiver is going to be bad because we will not be able to recreate the video. The other application between H2 and H4 is a file transfer. Sending a file, could be a large file. So one of them, H4, is downloading a file, maybe several gigabytes, so over a long period of time. But there's no strict time constraints. H4 doesn't care whether it takes 2 minutes, 3 minutes, or even 10 minutes. They've started the download, they've gone away, done something else. They know at some point in time it will eventually download. So what we want to do is give priority to the video application and give high priority to the video and lower priority to the download application. How do we do that? How do we give priority to our video application? Well, the router, R1, treats the video packets differently compared to the FTP, the download packets. And it's done in the queue. Just to give more space, I'll just draw the output queue because that's where the priority or the classification is performed. Again, packets come into the input queues and the router sends them to the appropriate output queue. And the blue packets are our video and the black packets are our download, FTP, file transfer. So the idea of giving priority in this simple case is that let the video packets jump to the head of the queue. Normally, our queuing mechanism is a first in, first out queue, a FIFO queue. That is, first packet to come into the queue goes to the head of the queue, and that is actually appended to the queue, and they'll be processed in order in a FIFO queue. The first one in will be the first one out, is the normal procedure. In this case, we're going to give priority to video packets and allow them to jump to the head of the queue. If at some point in time we have 4 packets in the queue, where the blue is the video packet and black is a FTP packet, this is, say, the first packet of the video, this is the first, second and third packets of our FTP application. At some point in time, they're the packets in the queue. Then the router simply processes them, but make sure it processes the video packets in the queue first. That is, process this packet and send it. By process, we send that packet. And then after we've sent the first packet, the remaining packets in the queue are FTP packets, so we just process them and send them in order. Send packet 1, black packet 1, black packet 2, and black packet 3. But if there's another 2 packets in the queue, 2 more video packets, the blue ones, then the router sends video packet 1. The next packet in the queue is FTP packet 1 and then FTP 2 and FTP 3. But it notices that there are also 2 more video packets in the queue. So after video packet 1 has been sent, it would in fact send video packet 2 and then video packet 3. So the order in which these are sent the first packet sent, the second packet sent, the third, fourth, fifth and sixth. So we simply give priority to the video packets in the queue at this point, such that those video packets should experience a shorter delay because they spend less time in the queue compared to our FTP packets. FTP. Blue one's a video. And the red numbers indicate the order in which those packets are sent in this simple example. Video packets sent first, and then any FTP packets in the queue are sent. And as new packets come in, if they're video packets, you think they just jump to the head of the queue. Or they, not to the head, they jump ahead of the FTP packets. But of course, still first in, first out for the video packets. So we now have a queuing mechanism that is not simply first in, first out. It's a priority queue, which gives priority to some of the packets. The impact of this is that if we look at the delay of those packets, how fast are we sending? If every packet was 1,500 bits, and we're sending at 1.5 megabits per second, then we'd send 1,000 packets per second. 1,000 times 1,500 is 1.5 million bits. So the rate at which we send packets out is 1,000 packets per second in this example, if every packet was the same size, which is not the case in practice, just for my calculations. That is, the time to send one packet takes 1 millisecond. That is, if we're sending 1,000 packets per second, then takes 1 second to transmit one packet. We transmit video packet 1. FTP packet 1 has to wait for other packets to be transmitted. How long does it have to wait? Well, let's say we transmit at time 0, transmit video packet 1. It takes 1 millisecond to transmit. If we're sending 1,000 packets per second, then to transmit one packet takes 1 millisecond. So we transmit video packet 1 at time equal to 1 millisecond. We can transmit the next packet. The next packet is video packet 2 in our case. And then 1 millisecond later, we can transmit the next packet, and it's video packet 3. And then 1 millisecond later, we can transmit the next packet, which, because there are no more video packets in the queue, we can start transmitting the FTP packets. FTP 1, 2 and 3. Each takes 1 millisecond to transmit. So the order in which the packets are transmitted. Now look at the queuing delay, assuming all of the packets arrived in there at the same time, just to keep the calculation simple. Video packet 1 is transmitted immediately. Say it has a delay, a queuing delay of 0. It doesn't have to wait in the queue. Video packet 2 needs to wait for video 1 to be transmitted. So if they all arrived at time 0, they instantly were all put in the queue at time 0. Video packet 1 is immediately transmitted. Video packet 2 has to wait 1 millisecond. It has a queuing delay of 1. Video packet 3 has to wait for 2 packets to be sent. It has a delay of 2. FTP packet has to wait for 3 to be sent, 4 and 5. So this is the queuing delay experienced by those individual packets. And you see that the FTP packets have a higher average queuing delay than the video packets. So by giving priority to our video packets, we've reduced the average queue delay for those video packets, but increased the average queuing delay for the FTP packets. Now, this is a very simple example. It's more complex because packets arrive at different times. In practice, it's much harder to calculate like in this simple way. And also in practice, packets may be different sizes. So the transmission times vary over time. But the point is, we give priority in the queue to some set of packets with the aim that they're transmitted first, such that it reduces the delay that they spend in the, or that they experience, the time they spend in the queue. Any questions on that part? How we reduce the delay of our packets? Clear? What's not clear? In the simplest form, we have a queue, and instead of treating it as a first in, first out queue, we treat different packets in the queue differently, putting them to the head of the queue when appropriate. Any questions? Okay. Don't worry too much about this calculation. That's not the point. It's just to, as a very simple example, to illustrate that, well, the video packets are sent first and then the FTP packets. Therefore, they'll have a shorter queue delay. FTP will have a larger queue delay. First in, last out. Which means basically transmit the last one first. Well, you try that on your Linux in the assignment. I'll show you some software where you can try it and see what happens. It won't be so good for most applications. But that raises a good point. We can have different algorithms for the queue. The basic algorithm is first in, first out, a FIFO queue. And that's usually a default algorithm. The queuing discipline, it's called, the way that we treat the queue. Here we've seen a priority queue where we give one set of packets priority over the others. We still treat all the FTP packets as first in, first out, and we treat the video packets as first in, first out, except the video packets can jump ahead of the FTP packets, so it's a different queuing mechanism. And we can have more complex queuing mechanisms depending upon what we want to achieve on the output. Let's extend the example. There's another packet in the queue, and our queue is full. Okay, so in this case, 7 packets in the queue already, and a new FTP packet arrives, FTP5. So there are 7 packets in the queue, it's full. FTP5 arrives, what happens? The queue is full, let's drop this packet. Okay, that would be the normal behaviour. Queue is full, a new one arrives, drop it. In fact, we don't have to drop the new one arrives. There are alternatives. What else could we do? Some cases we may drop a packet already in the queue and put this one in. It depends on what we want for our application. For example, drop the first packet in the queue. But for now, this is what's called a drop tail queue, or we drop the last packet arriving. Now, different case. Instead of FTP, video packet 4 arrives. What happens? What happens? Queue is full, 7 packets in the queue, video packet 4 arrives. What do we do? Now we can use a different mechanism for how to select packets to drop. By default, we'd think drop the packet that arrives. Here, let's try this approach. Drop the last FTP packet. Remove that packet from the queue. That's dropped. Video 4 goes in there. So again, here's a way to give priority to the video packets, the way that we drop packets. So 2 different approaches or 2 different algorithms. How do we select the packet to transmit in the queue such that we give a low delay? And how do we select the packets to drop such that we give low packet loss for our video application? So there's 2 different things there. How to select the ones to send and select the ones to drop. And again, there are different algorithms that can be more complex than that. Maybe drop the first FTP packets instead of the last one, depending on what performance those applications require. But that's how we give priority to packets in router queues, and essentially give priority to packets in the internet. For this to work, the router needs to know something about the types of packets coming in. It needs to know which packet's video, which packet is FTP. Packets must be marked some way such that the router can recognize the class of service they should be allocated. That is, there must be some marking in these packets that arrive at the router such that it knows, okay, this is a video packet, it's going to go to the head of FTP packets. How do we know that? How do we know that? How do we differentiate between the types of packets? What do we use in general?
You can put something in the packet so that indicates the type of...
We could put something in the packet, but okay. Where? In the header? Okay. When you look at packets in Wireshark, can you see the different types of packets? Yes, some cases you'll see, okay, this is a DHCP packet, this is, or at least you can see this is a TCP packet. In some cases you'll see it's a web packet, HTTP. So the packet headers themselves give some information about the type of application being used. So we can use the packet header information. And so we will use that. Things like source and destination port numbers. If the destination is port 80, we know it's going to a web server. It's web traffic. But in addition, there's a special field in IP packets that we can make use of. It's called the type of service field or the Diffserv field. Do we have the IP header? Maybe not. If you go back to one of your lecture notes that shows the structure of the IP header, in the header fields there's one which is called Diffserv. In the old times it was called type of service, so you may refer to either of them. I can't remember what it looks like. Someone look in the lecture notes. I think we have a picture of the IP header in your lecture notes on one of the first lectures. Tell me which field it is. Or it's in the exam at the back. Look in the IP header. Diffserv, the third field. Version, header length, and then Diffserv. How many bits? 6 bits. So if you go and see on that diagram, you have the IP header, and there's the version of the protocol, the header length, and the one that we're interested in is called the Diffserv field. It's 6 bits in length. In the past, it was called the type of service field, TOS. We can put a special number in there to mark the packet. Put a number to indicate the priority that this packet will receive. So if our source application, when it creates the IP header, puts some value in the Diffserv field to indicate this is video priority, then when the router receives it, as it comes in, it looks at the Diffserv field. If it's video priority, it knows how to treat it. If it's a different priority, it will treat it differently. So that's one way that we can mark the packets. How do we classify packets? So we use the fields or we can use the Diffserv field to mark the packet. How do we classify packets? Same approach. For example, what if we want to provide the service that if the FTP application, in our example, belongs to a premium user, I want to get priority compared to all the students for my FTP download in the SIT network, or you pay more, you pay 2,000 baht per month for your internet access. Normal users pay just 500 baht per month. Because you're paying for higher quality of service, then we could give priority to packets based upon the user in that case. So we can classify packets based upon different criteria. Common criteria to classify packets, that is, what priority they should receive, is using this Diffserv field in the IP header. DSCP stands for Diffserv code point. I don't know if it's written in one of the slides. DSCP. The field in the IP header is either called the type of service field, the Diffserv field, or the Diffserv code point. It's just some number that indicates a class. And where the classes, some of the classes are listed here: control, video, voice, data, and background. We're usually in order. That is, the lowest priority or the lowest class is background. The next lowest is data, then voice, video, and control. where control is when we need to do special things in the network to control other network equipment. For example, configure a router. So we give a number to, so we have 6 bits here. We use those bits to indicate a number for the background traffic or the background class. Similar for data, voice, video. So that's one way to classify packets. Background is, for example, data that we want to send, but we don't care when it gets there. Let's say we want to do a backup of our system overnight. We don't care how long it takes to send the backup across the network, as long as it gets there. So if we're sending a 10 gigabyte backup across the network, we could treat that as background traffic. So I'm sending my 10 gigabytes at midnight. No one else is using the network, but then someone starts up their web application, which would be treated just simply as data. Let's give that data higher priority than the background so that their short web application can get their packets through, and then the background packets can keep going. So we can think that's the lowest priority. Data would be the normal priority, web, voice, say voice calls, video applications, and above that would be control. For example, I want to configure a router, something's gone wrong. I need to change the router to give priority in a different manner. Then those packets that allow me to configure the router should get the highest priority. Control traffic. There are other more fine classifications, finer detail. But they're common ones. How does it work? Well, you can think your application that generates the packet and sends it out. When it generates the packet, it sets the class. If it's a web application, it's the application or the operating system sets the class to data. If it's a Skype or a voice over IP application, it sets the class to voice and so on. So when your applications or your OS creates the IP packet, it sets a class by setting a value in the Diffserv code point in the IP header. And then when it gets to the router treats it based upon that class. The other thing we can do is based upon the addresses. If we want to treat packets differently based upon the users, we can use the destination and source addresses, both IP addresses and port numbers. Everything from Steve's computer, based on my IP address in the office, gets high priority. Everything from all student users gets low priority. So based upon IP addresses, we can identify users. And also we can do that based upon port numbers as well. So other criteria used to classify packets. Does your computer, when you connect to your ISP at home or even SIT, classify packets? Often not. What may be common is here are our home computers. We're using some ADSL connection to our ISP. Here's the ISP's router. So many home users connect into the router. And then we have the ISP's network. So the autonomous system. And then there's other routers for another autonomous system. So this is the network of the ISP, your local ISP. What can happen is that rather than having the end users classify packets, get the router at the start of the network to do it for us. So because the ISP knows about the individual customers, it knows the IP addresses of the customers. As a packet comes customer with IP address 1, the router knows that, okay, this customer is paying for a premium service. It knows its IP address. Let's mark the packet then we send into the internet based upon who it came from, based upon source address. So packets may be marked either by the source host, the computer that sends it, or by some entry point into the network. For example, the router of the ISP. So packets could be marked here or here. The ISP border router in this case. What's the problem with allowing the end hosts to mark packets? What's the problem with allowing end hosts to mark packets? Okay. You've got your computer on the ISP. I allow you to mark packets at any priority that you choose. What do? Mark the highest priority, okay? He considers only himself. So if we allow the end host to mark the packets, and we follow those markings, this user marks all its packets. Doesn't matter if it's voice, video, he doesn't care if it's some background transfer, he just marks it with the highest priority. If we allow that, and we follow those markings, then we're not going to achieve our objectives, because if everyone marks their packets with high priority, even if it's a low priority background packet, then we're not going to be able to differentiate the different services. So in practice, what happens is the ISP will mark packets. If you mark the packet high priority, the ISP may ignore that and change the marking to the priority that it thinks the packet belongs to. If you're a premium user, maybe you get high priority. If it recognises it's a voice packet, it may get the voice class. Otherwise, it may just get a default marking. So in practice, normally the ISP or a border router will do the marking so that we don't have individuals selecting any marking that they like. So either the source host or some router marks packets. Yeah?
If ISP router don't care the mark from the end user, how the ISP router know the type of the packet, voice or data?
So if the ISP router is going to mark the packet, it needs to know what type of packet it is. If it's a voice or video. So there we need to do some inspection of the packet. For example, look at the packet headers, like the transport protocol being used, the application protocol, the port numbers. For example, if it's destination port number 80, HTTP packet, then we can mark it as data because it's just web traffic. Because different voice over IP servers use different port numbers and different transport protocols, if we can try and detect if it's a voice packet. So looking at the header structure is a way to classify into different applications.
Does it look at the data too?
That's up to how accurate we want to be in the classification. That is, looking at the header can tell us in some cases what type of application is being used. Normally it doesn't need to look in the data. The more we look into the packet, the longer it takes for the router to process that packet. That's the problem. It becomes more complex. So the idea is the router looks at the packet and tries to classify what type of application it is, and therefore what class of service that packet should be treated with. When packets are marked, routers apply some queuing mechanism, some queuing discipline to give priority to packets. We've said that the default is first in, first out, but there are other queuing mechanisms to give priority to packets. Like we saw over here, the video packets got priority, went ahead of the FTP packets. And there are many different queuing mechanisms. And to study the mathematics of the queuing schemes is probably a complete another course. And it becomes a policy decision of the ISP as to what priority to give, based upon their business model and based upon, say, what the customer is classified, a premium user or whichever. Another part is what happens if packets start to exceed some agreed upon values. Normally what we do is, if we have a premium user, that user pays some extra amount per month to get premium service, but it may be there may be some contract that says, okay, you will get for your voice traffic highest priority. You pay extra per month. If you pay the normal price, every packet you send is treated the same. If you pay the extra price, the premium price, then there may be some clause in the contract that says all of your voice packets will get classified as voice priority above normal traffic, and if you send video traffic then at a rate of 1 megabit per second, then that will be marked as video priority. That is, all your voice will be marked in the voice class. If you send video at 1 megabit per second, that will be classed in the video class. So there's some agreement between the user and the operator as to what service it will get. What happens if the user doesn't follow that agreement and they send more into the network than they've agreed upon? Then there are some ways to measure how much a user is sending, to do some metering of the traffic and policing, monitoring what the user is doing, and if they exceed what they said they would offer into the network, then to do something about it. We were not going to detail how that works, but as a simple example, let's say there's an agreement that the user will send video at 1 megabit per second. But if the video starts sending higher than 1 megabit per second, at 1.1 megabit per second, 1.2, it starts to exceed what it agreed upon, then either maybe there's some problem in the source application, or even it's malicious behaviour, it's someone trying to exceed what they've paid for. Then the operator, the ISP, will do some measurements of how fast that application is sending, some metering, and if it starts to exceed some values, it may start to police and drop packets, for example. If the application starts sending higher than 1 megabit per second over a period of 5 seconds, start to drop some of the packets so that it comes down to 1 megabit per second. It's a simple case.
How we can control the source process such as the video application with UDP, so they send as fast as we can.
Normally, say a video application, if you use UDP, the video application controls how much it sends. So a video records your video from the webcam. It, say, at some resolution, it converts the frames of that video into packets and sends those packets. If you increase the resolution, so you have a high definition webcam, then it will send packets faster across the network, or it will send more across the network. You do not control that, the application controls that. If you want the highest definition, you have very high definition webcam, then it will send more into the network. So the problem with that is that, yeah, if there's an agreement with you and the ISP that says, okay, your video will send 1 megabit per second into the network, which is, okay, standard definition, some resolution of video, but you raise the resolution to a higher resolution, high definition, and it starts sending 2 megabits per second into the network, when you've said you'll only send 1, then that's when the ISP at the router, it's measuring how much you're sending into the network. There's an agreement that say you will send 1, you're starting to send 1, 1.5, 2 megabits per second. The router is monitoring this. If you start to exceed that amount for some period of time, it simply starts to drop your packets, drop you down to 1 megabit per second. And of course that will affect your application and you won't do it again the next time. So service differentiation, Diffserv is the short name. We simply use queuing mechanisms to give priority to packets, where the priority is chosen based upon the marking of those packets, which is done at the source host or at some edge router, based upon the user and the type of application being used. And the queuing mechanism is about which packets are sent first and which packets are dropped first. So we can have different algorithms there to achieve some goal of giving a certain bandwidth, some delay or some jitter characteristic. The problem with service differentiation is we cannot guarantee performance. Coming back to our simple network, host 1 sending to host 3 a video application, host 2 to host 4 another video application. Our bottleneck link has a capacity of 1.5 megabits per second. In my slide I say video, on this diagram it says audio. Okay, let's change audio to video, it doesn't matter. But they're both sending at a rate of 1 megabit per second. Our bottleneck only supports 1.5. What happens? What happens in this case? We mark the packets as video. They both come into the router, video from 2 different users. If they're treated the same, then, or no matter what happens, packets are going to be dropped. 2 megabits per second coming into the router, 1.5 going out. Some packets have to be dropped. And if they are treated the same, that is video 1 and video 2 given the same priority, then packets from both video sessions are going to be dropped. Video sending at 1.5 megabits per second is going to receive at 750 kilobits per second, and video 2 the same. There's no guarantee that packets will not be dropped. There's no guarantee that the delay will be fixed. There's no guarantee of the throughput that you'll receive with service differentiation. That's the problem. But we can differentiate between different applications. We can give priority, but not guarantees. And for those that were here at the start of the lecture, that comes back to our example with a policeman. He needs to drive into Bangkok. We need to minimise the delay. When he gets to traffic lights, he drives around some cars on the footpath to get through the traffic lights rather than having to wait. But there's no guarantee that his delay will be a certain amount to get from source to destination. That's the problem. He still may be delayed in some cases. So we lead to the alternative approach, where we close down all the roads, don't let anyone on the roads, make all the traffic lights green, and the policeman goes from source to destination at 150 kilometres per hour at maximum speed. So there, the delay is guaranteed. It can be calculated in advance. We provide guaranteed or hard quality of service. The way we do that is that we reserve resources along the path. The only way to guarantee that the application or the user will have sufficient resources is to reserve them in advance. The resources, link bandwidth. We have a link bandwidth or a capacity of 1.5 megabits per second. At the router, reserve 1 megabit per second for our video application. So of that 1.5, 1.5 is reserved for a video application, as an example. Reserve queue space. There will always be 5 of the 7 slots allocated to our video application, such that we can manage the packets that are dropped. and reserve processing time. That is, the processor in the router reserves some time so we can also always process packets from our video application, so we can guarantee for an individual application that it gets a particular delay, a particular drop rate, and a particular bandwidth or throughput. So by reserving resources, we can guarantee those resources, and guarantee performance. Of course, we cannot over-reserve. Our router here has an output capacity of 1.5 megabits per second. The first application to request use of the network reserves 1 megabit per second. Okay? It needs 1 megabit per second to work well for the user, so it reserves 1 megabit per second of this link. So for the reserved resources, the reservations, video 1 is reserved 1 megabit per second. And then some other user starts another application, a voice application, reserves 200 kilobits per second. And when I say reserves, it essentially asks the router, I want 200 kilobits per second, can you provide me that? The router says, okay, I've reserved 1 out of 1.5, I have 0.5 remaining. Okay, yes, I'll accept your voice application. So the voice application is reserved 200 kilobits per second. Then sometime later, while those are in progress, another application has started, video 2, wants also 1 megabit per second, asks the router, I want to reserve 1 megabit per second. The router says no. It cannot reserve 1 megabit per second, it only has 300 kilobits per second remaining, unreserved. So that application would be rejected from the network. It would not be able to start. If it wants to start and reserve 1 megabit per second, when you start the application, it goes through some process to try to reserve that 1 megabit per second. If a router doesn't have enough capacity, it sends back some rejection message saying, no, I reject your reservation, and the application will not start. So, of course, we cannot over-reserve. If the router reserved said, yes, I will accept video 2, then we will no longer have guarantees. Because if we accept 1 plus 1 plus 200 kilobits per second, 2.2 kilobits per second, and we only support 1.5, again, we cannot guarantee service to all of them. So the only way to guarantee is to accept reservations that are within our limits. So we have what's called admission control. Admit the applications based upon the request for resources. If the network, or more specifically the routers, can support the request of resources, if they have enough capacity, if they have enough queue space, they can accept the connection. If not, they reject. That is, they either admit the application into the network or do not. Admission control. There's a protocol for how to reserve resources. It's called the Resource Reservation Protocol, Rsvp. So how does your application ask a router to reserve this resource? There's a protocol that does that for us. In the internet, the name of the architecture that provides this hard quality of service is called integrated services, IntServ. The previous one was called differentiated services.
Is it possible to reserve the resource to all routers such as I want to connect to the USA, so it have to pass through many routers.
It's not just possible, it's required. Let's say, so the question is, do you reserve through multiple routers? Well, yes, you should reserve the resources through all routers in the path. Because if I reserve the resources at the first router, that's fine. But if the second router will not offer those resources that I need, if the second router or some other router in the path cannot offer me 1 megabit per second, then my reservations are of no use because I may not be guaranteed that 1 megabit per second down in the path. So in fact, we need to reserve resources from the source through all routers to the destination across the entire path. Same with our policemen or our VIP driving into Bangkok. It's okay if they stop the traffic at one set of intersection. To get this guaranteed delay, you need to stop the traffic all the way from source to destination. You need to reserve the resources all the way. Reserving just a part is insufficient. And that's the problem with this approach. It's very complex to do that. It means I need to find the path from source to destination, from here to the US, and communicate with all the routers along that path, get them to agree upon my request before I can start sending data. The name of the system that does this is called Integrated Services, or IntServ. Normally applied at the flow level on individual applications. It uses Rsvp. Here's our two applications. The blue computers want to communicate. Here's our internet with a set of routers. Before our application can send data, so when I start my video application, it does this special Rsvp request. It sends a request to the first router saying, I want to reserve these resources, 1 megabit per second. This first router either accepts or rejects. If it accepts, it sends the request to the next router in the path. That accepts or rejects, keeps going. And the receiving application either accepts or rejects the reservation request. And then if everything's accepted, a response comes back saying, you've now set up a path. The resources you asked for are reserved along that path. You're guaranteed to get 1 megabit per second, packet loss rate below some value, packet delay of some value. And then the application starts sending data. That's the very basics of resource reservation. Send a request to all the routers in the path, asking to reserve resources, allocating the 1 megabit per second at each router, as an example, or allocating queue space at each router. And if every router accepts that, then we can start our application. If one of them rejects, if this router doesn't have enough capacity to reserve that requested 1 megabit per second, then the reject message will come back and the application cannot send data. What does the application do in that case? Maybe it will try and set up another reservation at a lower performance requirement, maybe at 750 kilobits per second. Wow, only one slide left, good. So that's the basics of IntServ. How's all the rest implemented? The same as Diffserv. We still use queuing mechanisms to give priority in IntServ. The main difference is that we reserve the resources in advance. Once we reserve 1 megabit per second for the video, this router uses queuing mechanisms, queuing algorithms, to make sure that the video packets achieve this 1 megabit per second. Or if we reserve and say that the video application is going to get less than 1% of packet loss, okay, as part of the agreement, no more than 1% of packets will be lost, then there's enough space allocated for the video applications in the queue, and the queuing scheme makes sure that less than 1% of the video packets are lost. So if a packet needs to be lost in that case, it needs to be dropped, drop the other applications first. Make sure the video packets do not get dropped. So again, the same as Diffserv, we use queuing mechanisms and the algorithms to drop packets to provide the quality of service. The main difference is in IntServ, or guaranteed quality of service, we reserve the resources in advance. So, in summary, what have we got today? To provide quality of service, we're trying to give different users, different applications, different levels of service, different priorities in the network. Two basic approaches: soft quality of service, or service differentiation, and hard quality of service, or guaranteed QoS. The name of the system in the internet for service differentiation is Diffserv, and for hard QoS is IntServ, integrated services. Both of them use the routers and the queuing mechanisms at the routers to provide some quality of service, to differentiate packets, give priorities, to manage the queue, manage the packet drop rate. In service differentiation, we normally give relative priorities to classes of traffic. All voice packets give priority 1. All data packets get priority 2. So it's based on classes of traffic. In guaranteed quality of service, we normally do it based upon flows. All applications from user 1 that are voice applications get one level of service. From user 1 using video applications gets a different level of service. So it's based on individual flows, individual applications, as opposed to a collection of applications or flows. That is, guaranteed quality of service is a much finer level of detail of guaranteeing. If I have two video applications running at the same time, I don't know why, but I'm streaming two video applications at the same time, then with guaranteed quality of service, I could give each of them different performance. With service differentiation, they will just both be treated as video and given the same performance. All the video are treated the same in service differentiation. Guaranteed quality of service uses the same principles of old telephone networks. Before you start sending your data, you set up the connection, guarantee the resources. Before you start talking on the phone, it sets up the connection. Service differentiation is much simpler in large networks. Because we operate just on classes of traffic, not individual flows, and because we don't need complex signaling of setting up the connection of reserving resources. We don't need Rsvp. We don't need all the routers to agree. It becomes much simpler. We just need routers to give priorities based upon classes. But the problem with service differentiation, it doesn't guarantee quality of service. Your video application still may have packets dropped. It may not get the 1 megabit per second in some cases. Guaranteed QoS guarantees the performance, but is more complex. Today, neither approach is widely deployed. That is, my computer at home or at work doesn't use either of them. It doesn't mark packets. Or if it does, usually it makes no difference. But in some internet service providers, in their core networks, they will use often service differentiation. So inside some ISPs, QoS is used. And sometimes there's even combinations of these. Some of the names, MPLS is an example. But usually the end users today do not have direct access to the mechanisms. It makes no difference if I mark the packet as voice, video, or background. It depends on what my ISP does. And one ISP may provide service differentiation, another may not. It depends upon your ISP. Usually within the core of the internet they do use quality of service control, but not the end consumer ISPs. But between ISPs often they will use this. So that covers the basics of quality of service. You should understand what we're trying to achieve with quality of service, giving priority to different applications or classes of applications, and how we can achieve that. In particular, what we can do at routers. Basically, we use different queuing mechanisms, and the difference between soft and hard quality of service, the advantages and disadvantages. That finishes for this topic. Next week we'll move on to and look at voice over IP, streaming audio and video, and IPTV, multimedia applications. After that, there's just one topic remaining, peer-to-peer applications. So not long to go. Any questions? If you have questions about the assignment, then come and see me during the week, or at least ask me next Wednesday. You only have, 2 weeks remaining? You need to get started on that. There are some